them for our ranking. Interestingly, the majority of our code concerns the interaction with the API, in which we have to get our API address and authentication details, set up a session for interacting with the API, and include extra functionality for handling details of the API, such as pagination. One way of dealing with the complexity of interacting with the API is encapsulating all this code into a reusable Airflow hook. By doing so, we can keep all the API-specific code in one place and simply use this hook in different places in our DAGs, which allows us to reduce the effort of fetching ratings to something like this. Hooks also allow us to leverage Airflow's functionality for managing connection credentials via the database and UI, meaning that we don't have to manually supply our API credentials to our DAG. In the next few sections, we'll explore how to write a custom hook and set about building a hook for our movie API. Section 8.2.1, Designing a Custom Hook. In Airflow, all hooks are created as subclasses of the abstract base hook class. To start building a hook, we need to define a dunderInit method that specifies which connection the hook uses, if applicable, and any other extra arguments our hook might need. In this case, we want our hook to get its connection details from a specific connection, but don't need any extra arguments. Most Airflow hooks are expected to define a get_con method, which is responsible for setting up a connection to an external system. In our case, this means that we can reuse most of our previously defined _get_session function, which already provides us with a pre-configured session for the movie API. That means a naive implementation of get_con could look something like this. However, instead of hard-coding our credentials, we prefer to fetch them from the Airflow credentials store, which is more secure and easier to manage. To do so, we first need to add our connection to the Airflow metastore, which we can do by opening the Admin Connections section using the Airflow web UI and clicking Create to add a new connection. In the Connection Create screen, figure 8.5, we need to fill in the connection details of our API. In this case, we'll call the connection MovieLens. We'll use this ID later in our code to refer to the connection. Under Connection Type, we select HTTP for our REST API. Under Host, we need to refer to the host name of the API in our Docker Compose setup, which is MovieLens. Next, we can optionally indicate what schema we'll use for the connection, HTTP, and add the required login credentials, user, Airflow, password, Airflow. Finally, we need to say under which port our API will be available, which is port 5000 in our Docker Compose setup, as we saw earlier when manually accessing the API. Now that we have our connection, we need to modify our get_con to fetch the connection details from the metastore. To do so, the basehook class provides a convenience method called get_connection, which can retrieve the connection details for a given connection ID from the metastore. This connection configuration object has fields that map to the different details we just filled in when creating our connection. As such, we can use the config object to start determining the host port and user password for our API. First, we use the schema host and port fields to determine our API URL as before. Note that we define default values in our class, similar to the constants we defined before, in case these fields are not specified in the connection. If we want to require them to be specified in the connection itself, we can raise an error instead of supplying defaults. Now that we have obtained our base URL from the metastore, we only need to configure authentication details in our session. This gives us the following new implementation for get_con. One drawback of this implementation is that each call to get_con will result in a call to the Airflow metastore, as get_con needs to fetch the credentials from the database. We can avoid this limitation by also caching session and base_URL on our instance as protected variables. This way, the first time get_con gets called, self._session is none. So we end up fetching our connection details from the metastore and setting up our base URL and session. By storing these objects in the _session and _base _URL instance variables, we make sure that these objects are cached for later calls. As such, a second call to get_con will see that self._session no longer is none, and will return a cached session and base URL. Note: personally, we're not fans of using the get_con method directly outside of the hook, even though it is publicly exposed, because this method exposes the internal details of how your hook accesses the external system, breaking encapsulation. This will give you substantial headaches if you ever want to change this internal detail, as your code will be strongly coupled to the internal connection type. This has been an issue in the Airflow codebase as well. For example, in the case of the HDFS hook, where the implementation of the hook was tightly coupled to a Python 2.7 only library, Snakebite. Now that we have completed our implementation of get_con, we are able to build an authenticated connection to our API. This means we can finally start building some useful methods into our hook, which we can then use to do something useful with our API. For fetching ratings, we can reuse the code from our previous implementation, which retrieved ratings from the /ratings endpoint of the API and used our get_with_pagination function to handle pagination. The main difference from the previous version is that we now use get_con within the pagination function to get our API session. Altogether, this gives us a basic Airflow hook that handles connections to the Movie Lens API. Adding extra functionality, other than just fetching ratings, can be easily done by adding extra methods to the hook. Although it may seem like a lot of effort to build a hook, most of the work was shifting around the functions we wrote before into a single consolidated hook class. An advantage of our new hook is that it provides nice encapsulation of the Movie Lens API logic in a single class, which is easy to use across different DAGs. Section 8.2.2 Building our DAG with the Movie Lens hook. Now that we have our hook, we can start using it to fetch ratings in our DAG. However, first we need to save our hook class somewhere so that we can import it into our DAG. One way is by creating a package in the same directory as our DAG's folder, and save our hook in a hooks.py module inside this package. Footnote 5. We'll show another package-based approach later in this chapter. Once we have this package, we can import our hook from the new custom package, which contains our custom hook code. After importing the hook, fetching ratings becomes quite simple. We only need to instantiate the hook with the proper connection ID, and then call the hook's get_ratings method with the desired start-end dates. This gives back a generator of rating records, which we then write to an output JSON file. To use the hook in our DAG, we still need to wrap this code in a Python operator that takes care of supplying the correct start-end dates for the given DAG run, as well as actually writing the ratings to the desired output file. For this, we can essentially use the same _fetch_ratings function we defined for our initial DAG, changing the call to _get_ratings with the call to our new hook. Note that we added the parameter con_id to fetch_ratings, which specifies the connection to use for the hook. As such, we also need to include this parameter when calling _fetch_ratings from the Python operator. This gives us the same behavior as before, but with a much simpler and smaller DAG file, as most of the complexity surrounding the Movie Lens API is now outsourced to the Movie Lens hook. Section 8.3 Building a Custom Operator. Although building a Movie Lens hook has allowed us to move a lot of complexity from our DAG into the hook, we still have to write a considerable amount of boilerplate code for defining start-end dates and writing the ratings to an output file. This means that if we want to reuse this functionality in multiple DAGs, we will still have some considerable code duplication and extra effort involved. Fortunately, Airflow also allows us to build custom operators, which can be used to perform repetitive tasks with a minimal amount of boilerplate code. In this case, We could, for example, use this functionality to build a movie lens fetch ratings operator, which would allow us to fetch movie ratings using a specialized operator class. Section 8.3.1 Defining a custom operator. In Airflow, all operators are built as subclasses of the base operator class. Any arguments specific to your operator, such as con_id in this example, can be specified explicitly in the dunder_init constructor method. How you use these arguments is, of course, up to you. Operator-specific arguments vary between different operators, but typically include connection IDs for operators involving remote systems, and any details required for the operation, such as start-end dates, queries, etc. The base operator class also takes a large number of mostly optional generic arguments that define the basic behavior of the operator. Examples of generic arguments include the task_ID the operator created for the task, but also many arguments such as retries and retry_delay that affect the scheduling of the resulting task. To avoid having to list all these generic tasks explicitly, we use Python's **quargs syntax to forward these generic arguments to the dunder_init of the base operator class. Thinking back to earlier DAGs in this book, you may remember that Airflow also provides the option of defining certain arguments as default arguments for the entire DAG. This is done using the default_args parameter to the DAG object itself. To ensure that these default arguments are applied to your custom operator, Airflow supplies the apply_defaults decorator, which is applied to the dunder_init method of your operator, as shown in our initial example. In practice, this means that you should always include the apply_defaults decorator when defining custom operators. Otherwise, you will inadvertently break this Airflow behavior for your operator. Now that we have our basic custom operator class, we still need to define what our operator actually does by implementing the execute method, the main method Airflow calls when the operator is actually being executed as part of a DAG run. As you can see, the execute method takes a single parameter, context, which is a dict containing all the Airflow context variables. The method can then continue to perform whatever function the operator was designed to do, taking variables from the Airflow context, such as execution dates, etc., into account. Section 8.3.2 Building an operator for fetching ratings. Now that we know the basics of building an operator, let's see how we can start building a custom one for fetching ratings. The idea is that this operator fetches ratings from the MovieLens API between a given start-end date and writes these ratings to a JSON file, similar to what our _fetch_ratings function was doing in our previous DAG. We can start by filling in the required parameters for the operator in its dunder_init method, which include the start-end dates, which connection to use, and an output path to write to. Next, we have to implement the body of the operator, which actually fetches the ratings and writes them to an output file. To do this, we can essentially fill in the execute method of the operator with a modified version of our implementation for _fetch_ratings. As you can see, porting our code to a custom operator required relatively few changes to our code. Similar to the _fetch_ratings function, this execute method starts by creating an instance of our MovieLens hook and using this hook to fetch ratings between the given start-end dates. One difference is that the code now takes its parameters from self, making sure to use the values passed when instantiating the operator. We also switched our logging calls to use the logger provided by the base operator class, which is available in the self.log property. Finally, we added some exception handling to make sure our hook is always closed properly, even if the call to get_ratings fails. This way, we don't waste any resources by forgetting to close our API sessions, which is good practice when implementing code that uses hooks. Using this operator is relatively straightforward, as we can simply instantiate the operator and include it in our DAG. A drawback of this implementation is that it takes predefined dates for which the operator will fetch ratings. As such, the operator will only fetch ratings for a single hard-coded time period, without taking the execution date into account. Fortunately, Airflow also allows us to make certain operator variables templatable, meaning that they can refer to context variables such as the execution date. To allow specific instance variables to be templated, we need to tell Airflow to template them using the templates_field class variable. This effectively tells Airflow that the variables _start, _date, _end, _date, and _output, _path, which are created in dunderinit, are available for templating. This means that if we use any Jinja templating in these string parameters, Airflow will make sure that these values are templated before our execute method is called. As a result, we can now use our operator with templated arguments as follows. This way, Airflow will fill in the values of the start of the execution window, ds, for the start date, and the end of the execution window, next_ds, for the end date. It will also make sure the output is written to a file tagged with the start of the execution window, ds. Section 8.4, Building Custom Sensors. With all this talk about operators, you may be wondering how much effort it takes to build a custom sensor. In case you skipped over them in previous chapters, a sensor is a special type of operator that can be used to wait for a certain condition to be fulfilled before executing any downstream tasks in the DAG. For example, you may want to use a sensor for checking if certain files or data are available in a source system before trying to use the data in any downstream analysis. Regarding their implementation, sensors are very similar to operators, except that they inherit from the base sensor operator class instead of the base operator. As the name suggests, this shows that sensors are in fact a special type of operator. The base sensor operator class provides the basic functionality for a sensor and requires sensors to implement a special poke method rather than the execute method. The signature of the poke method is similar to execute in that it takes a single argument containing the Airflow context. However, in contrast to the execute method, poke is expected to return a Boolean value that indicates if the sensor condition is true. If it is, the sensor finishes its execution, allowing downstream tasks to start executing. If the condition is false, the sensor sleeps for several seconds before checking the condition again. This process repeats until the condition becomes true or the sensor hits its timeout. Although Airflow has many built-in sensors, you can essentially build your own to check any type of condition. For example, in our use case, we may want to implement a sensor that first checks if rating data is available for a given date before continuing with the execution of our DAG. To start building our movie lens ratings sensor, we first need to define the dunderinit of our custom sensor class, which should take a connection ID, the species which connection detail to use for the API, and a range of start-end dates, which specifies for which date range we want to check if there are ratings. This would look something like the following. After specifying the constructor, the only thing we need to implement is our poke method. In this method, we can check if there are ratings for a specific date range by simply requesting ratings between the given start-end dates that return true if there are any records. Note that this does not require fetching all rating records. We only need to demonstrate that there is at least one record in the range. Using our movie lens hook, implementing this algorithm is pretty straightforward. First, we instantiate the hook and then call get_ratings to start fetching records. As we are only interested in seeing if there is at least one record, we can try calling next on the generator returned by get_ratings, which will raise a stop iteration if the generator is empty. As such, we can test for the exception using try except, returning true if no exception is raised, and false if it is, indicating that there were no records. Note that the reuse of our movie lens hook makes this code relatively short and succinct, demonstrating the power of containing the details of interacting with the movie lens API within the hook class. This sensor class can now be used to make the DAG check and wait for new ratings to come in before continuing with the execution of the rest of the DAG. Section 8.5, Packaging your components. Up to now, we've relied on including our custom components in a sub-package within the DAGs directory to make them importable by our DAGs. However, this approach is not necessarily ideal if you want to be able to use these components in other projects, want to share them with other people, or want to perform more rigorous testing on them. A better approach for distributing your components is to put your code into a Python package. Although this requires a bit of extra overhead in terms of setup, it gives you the benefit of being able to install your components into your Airflow environment, as with any other package. Moreover, keeping the code separate from your DAGs allows you to set up a proper CI/CD process for your custom code and makes it easier to share, collaborate on the code with others. Section 8.5.1 Bootstrapping a Python Package. Unfortunately, packaging can be a complicated topic in Python. In this case, we'll focus on the most basic example of Python packaging, which involves using setup tools to create a simple Python package. Using this approach, we aim to create a small package called Airflow_MovieLens, which will contain the hook, operator, and sensor classes written in the previous sections. Footnote 6. More in-depth discussions of Python packaging and different packaging approaches are outside the scope of this book and explained more elaborately in many Python books and/or online articles. To start building our package, let's first create a directory for our package. Next, let's start including our code by creating the base of our package. To do this, we'll contain a src subdirectory in our Airflow_MovieLens directory and create a directory Airflow_MovieLens, the name of our package, inside this src directory. To make Airflow_MovieLens into a package, we also create a dunderinit.py file inside the directory. Footnote 7. Technically, the dunderinit.py file is no longer necessary with PEP 420, but we like to be explicit. Next, we can start including our code by creating the files hooks.py, sensors.py, and operators.py in the Airflow_MovieLens directory, and copying the implementations of our custom hook, sensor, and operator classes into their respective files. Once done, you should end up with a result that looks something like this. Now that we have the basic structure of our package, all we need to do to turn this into a package is to include a setup.py file, which tells setup tools how to install it. A basic setup.py file typically looks something like the following listing. The most important part of this file is the call to setuptools.setup, which gives setup tools detailed metadata about our package. The most important fields in this call are as follows. Name defines the name of your package, what it will be called when installed. Version, the version number of your package. Install_requires, a list of dependencies required by your package. Packages, package_dir, tells setup tools which packages to include when installing and where to look for these packages. In this case, we use a src directory layout for our Python package. Footnote 8. See this blog for more details on src versus non-src based layouts. See this link. Additionally, Setup Tools allows you to include many optional fields for describing your package, including the following. Footnote 9. For a full reference of parameters that you can pass to setuptools.setup, please refer to the Setup Tools documentation. Author. The name of the package author, you. Author_email. Contact details for the author. Description. A short, readable description of your package, typically one line. A longer description can be given using the long_description argument. URL. Where to find your package online. License. The license under which your package code is released, if any. Looking at the setup.py implementation, this means that we tell setup tools that our dependencies include Apache-Airflow and requests, that our package should be called Airflow_MovieLens with a version of 0.1, and that it should include files from the Airflow_MovieLens package situated in the src directory, while including some extra details about ourselves and the package description license. Once we have finished writing our setup.py, our package should look like this. This means we now have a setup for our basic airflow_movie lens Python package, which we can try installing in the next section. Of course, more elaborate packages will typically include tests, documentation, and so on, which we don't describe here. If you want to see extensive setups for Python packaging, we recommend checking out the many templates available online. For example, here, which provide excellent starting points for bootstrapping Python package development. Section 8.5.2, Installing your package. Now that we have our basic package, we should be able to install airflow_movie lens into our Python environment. You can try this by running pip to install the package in your active environment. Once pip is done installing your package and dependencies, you can check whether your package was installed by starting Python and trying to import one of the classes from your package. Deploying your package to your Airflow environment shouldn't require much more effort than installing your package in Airflow's Python environment. However, depending on your setup, you should make sure that your package and all its dependencies are installed in all of the environments Airflow uses, that is, the scheduler, web server, and worker environments. Distribution of your package can be handled by either installing directly from a GitHub repository or by using a pip package feed such as pypi, or a private feed, or by installing from a file-based location, as we initially did here. In the latter case, you do need to make sure that the Airflow environment can access the directory from which you want to install the package. Summary. You can extend Airflow's built-in functionality by building custom components that fit your specific use cases. In our experience, two use cases in which custom operators are particularly powerful are as follows. Running tasks on systems that are not natively supported by Airflow, for example, new cloud services, databases, etc. Providing operators, sensors, hooks for commonly performed operations, such that these are easy to implement by people in your team across DAGs. Of course, this is by no means an exhaustive list, and there may be many other situations in which you would want to build your own components. Custom hooks allow you to interact with systems that do not have support built into Airflow. Custom operators can be created to perform tasks that are specific to your workflows and are not covered by built-in operators. Custom sensors allow you to build components for waiting on external events. Code containing custom operators, hooks, sensors, and so on can be structured by implementing them in a distributable Python library. Custom hooks, operators, sensors require you to install them with their dependencies on your Airflow cluster before they can be used. This can be tricky if you do not have permission to install software on the cluster, or if you have software with conflicting dependencies. Some people prefer to rely on generic operators, such as the built-in Docker operator and the Kubernetes pod operator to execute their tasks. An advantage of this approach is that you can keep your Airflow installation lean, as Airflow is only coordinating containerized jobs. You can keep all dependencies of specific tasks with the container. We'll focus on this approach further in a future chapter. Chapter 9. Testing. This chapter covers testing Airflow tasks in a CI/CD pipeline, structuring a project for testing with PyTest, mimicking a DAG run to test tasks that apply templating, faking external system events with mocking, testing behavior in external systems with containers. In all previous chapters, we focused on various parts of developing Airflow. So how do you ensure the code you've written is valid before deploying it into a production system? Testing is an integral part of software development, and nobody wants to write code, take it through a deployment process, and keep their fingers crossed for all to be okay. Such a way of development is obviously inefficient and provides no guarantees on the correct functioning of the software, both in valid and invalid situations. This chapter will dive into the gray area of testing Airflow, which is often regarded as a tricky subject. This is because of Airflow's nature of communicating with many external systems and the fact that it's an orchestration system, which starts and stops tasks performing logic, while Airflow itself often does not perform any logic. Section 9.1. Getting started with testing. Tests can be applied on various levels. Small individual units of work, that is, single functions, can be tested with unit tests. While such tests might validate the correct behavior, they do not validate the behavior of a system composed of multiple such units altogether. For this purpose, we write integration tests, which validate the behavior of multiple components together. In testing literature, the next used level of testing is acceptance testing, evaluating fit with business requirements, which does not apply to this chapter. Here, we will dive into unit and integration testing. Throughout this chapter, we demonstrate various code snippets written with PyTest. See this link. While Python has a built-in framework for testing named Unit Test, PyTest is one of the most popular third-party testing frameworks for various features, such as fixtures, which we'll take advantage of in this chapter. No prior knowledge of PyTest is assumed. Since the supporting code with this book lives in GitHub, we'll demonstrate a CI/CD pipeline running tests with GitHub Actions. See this link, the CI/CD system that integrates with GitHub. With the ideas and code from the GitHub Actions examples, you should be able to get your CI/CD pipeline running in any system. All popular CI/CD systems, such as GitLab, Bitbucket, CircleCI, Travis CI, and so on, work by defining the pipeline in YAML format in the root of the project directory, which we'll also do in the GitHub Actions examples. Section 9.1.1. Integrity Testing All DAGs. In the context of Airflow, the first step for testing is generally a DAG integrity test, a term made known by a blog post titled Data's Inferno, 7 Circles of Data Testing Hell with Airflow. See this link. Such a test verifies all your DAGs for their integrity, that is, the correctness of the DAG, for example, validating if the DAGs do not contain cycles, if the task IDs in the DAG are unique, etc. The DAG integrity test often filters simple mistakes. For example, a mistake is often made when generating tasks in a for loop with a fixed task ID instead of a dynamically set task ID, resulting in each generated task having the same ID. Upon loading DAGs, Airflow also performs such checks itself and will display an error if found. Figure 9.1. To avoid going through a deployment cycle to discover in the end your DAG contains a simple mistake, it is wise to perform DAG integrity tests in your test suite. The following DAG in listing 9.1 would display an error in the UI because there is a cycle between T1, T2, T3, back to T1. This violates the property that a DAG should have finite start and end nodes. Now, let's catch this error in a DAG integrity test. First, let's install PyTest. This gives us a PyTest CLI utility. To see all available options, run pytest-help. For now, there's no need to know all the options. Knowing you can run tests with PyTest, file/directory, where the directory contains test files, is enough. Let's create such a file. A convention is to create a tests/folder at the root of the project that holds all the tests and mirrors the same directory structure as in the rest of the project. So, if your project structure is like the one shown in figure 9.2, then the test/directory structure would look like the one shown in figure 9.3. Footnote 1. PyTest calls this structure tests outside application code. The other supported structure by PyTest is to store test files directly next to your application code, which it calls tests as part of your application code. Note all tests mirror the file names that are presumably being tested, prefixed with test_. Again, while mirroring the name of the file to test is not required, it is an evident convention to tell something about the contents of the file. Tests that overlap multiple files or provide other sorts of tests, such as the DAG integrity test, are conventionally placed in files named according to whatever they're testing. However, the test_ prefix here is required. PyTest scans through given directories and searches for files prefixed with test underscore or suffixed with underscore test. Also note there are no dunderinit.py files in the tests/directory. The directories are not modules, and tests should be able to run independently of each other without importing each other. PyTest scans directories and files and auto-discovers tests. There's no need to create modules with dunderinit.py files. Footnote 2. Test discovery settings are configurable in PyTest if you want to support, for example, test files named check_star. Let's create a file named tests/dags/test_dag_integrity.py. Here we see one function named test_dag_integrity, which performs the test. The code might look a little obscure at first sight, so let's break it down. Remember the folder structure previously explained? There's a dags/folder that holds all DAG files, and the file test_dag_integrity.py, which lives in tests/dags/test_dag_integrity.py. This DAG integrity test is pointed to a folder holding all DAG files, in which it then searches recursively for star.py files, figure 9.4. The dir name returns the directory of test_dag_integrity.py, and then we browse two directories up, first to tests/ second to the root, and from there we search for anything matching the pattern dags/star/star.py. Star will search recursively. So DAG files in, for example, dags/dir1/dir2/dir3/mydag.py will also be found. Finally, the variable dag_files holds a list of files found in dags/ ending in .py. Next, the decorator at pytest.mark.parameterize runs the test for every found Python file, figure 9.5. The first part of the test is a little obscure. We won't go into details, but it boils down to loading and executing the file, just like Python itself would do, and extracting the DAG objects from it. Now that the DAG objects are extracted from the file, we can apply certain checks on it. In the code, we applied two checks. First was an assertion, assert dag_objects, checking if DAG objects were found in the file, making it successful. Adding this assertion validates all Python files found in /dags if they contain at least one DAG object. For example, scripts utility functions stored in /dags, in which no DAG objects are instantiated, therefore fail. Whether this is desirable is up to you, but having one directory holding only DAG files and nothing else does provide a clear separation of duties. The second check, for DAG in dag_objects, dag.test_cycle, validates whether there are no cycles in the DAG objects. This is called explicitly for a reason. Before Airflow 1.10.0, DAGs were checked for cycles with every change to their structure. This check becomes computationally heavier as more and more tasks are added. For DAGs with a large number of tasks, this became a burden, because for every new task, a DAG cycle check was performed, causing long reading times. Therefore, the DAG cycle check was moved to the point where DAGs are parsed and cached by Airflow into a structure called the DAG bag, such that the cycle check is performed only once after parsing the complete DAG, reducing reading time. As a result, it's perfectly fine to declare T1, T2, T1, and evaluate it. Only once a live running Airflow instance will read your script will it complain about the cycle. So to avoid going through a deployment cycle, we call test_cycle explicitly on each DAG found in the test. These are two example checks, but you can add your own, of course. If, say, you want each DAG name to start with import or export, you can check the dag_IDs. Now let's run the DAG integrity test. On the command line, run pytest, optionally hinting pytest where to search with pytest tests/ to avoid scanning other directories. The result of the test is quite lengthy, but typically you search for answers at the top and bottom. Near the top, you find which test failed, and at the bottom, answers why the test failed. This example shows us, as expected, a cycle was detected from T3 to T1. Upon instantiation of DAGs and operators, several other checks are performed out of the box. Say you are using a bash operator but forgot to add the required bash_command argument. The DAG integrity test will evaluate all statements in the script and fail when evaluating the bash operator. The DAG integrity test will encounter an exception and fail. With the DAG integrity test in place, let's run it automatically in a CI/CD pipeline. Section 9.1.2, Setting up a CI/CD pipeline. In a one-liner, a CI/CD pipeline is a system that runs predefined scripts when you make a change to your code repository. The continuous integration, CI, denotes checking and validating the changed code to ensure it complies with coding standards and a test suite. For example, upon pushing code, you could check for flake 8 at this link, pylint at this link, and black at this link, and run a series of tests. The continuous deployment, CD, indicates automatically deploying the code into production systems, completely automated and without human interference. The goal is to maximize coding productivity without having to deal with manually validating and deploying it. There is a wide range of CI/CD systems. In this chapter, we will cover GitHub Actions. See this link. The general ideas should apply to any CI/CD system. Most CI/CD systems start with a YAML configuration file in which a pipeline is defined, a series of steps to execute upon changing code. Each step should complete successfully to make the pipeline successful. In the Git repository, we can then enforce rules such as only merge to master with a successful pipeline. The pipeline definitions typically live in the root of your project. GitHub Actions requires YAML files stored in a directory, .github/workflows. With GitHub Actions, the name of the YAML doesn't matter, so we could create a file named airflow tests.yaml with the following content. The keywords shown in this YAML file are unique to GitHub Actions, although the general ideas apply to other CI/CD systems too. Important things to note are the tasks in GitHub Actions defined under steps. Each step runs a piece of code. For example, Flake 8 performs static code analysis and will fail if any issues are encountered, such as an unused import. On row 3, we state on:push, which tells GitHub to run the complete CI/CD pipeline every time it receives a push. In a completely automated CD system, it would contain filters for steps on specific branches, such as master, to only run steps and deploy code if the pipeline succeeds on that branch. Section 9.1.3, Writing Unit Tests. Now that we have a CI/CD pipeline up and running, which initially checks the validity of all DAGs in the project, it's time to dive a bit deeper into the Airflow code and start unit testing individual bits and pieces. Looking at the custom components demonstrated in Chapter 8, there are several things we could test to validate correct behavior. The saying goes, never trust user input. So we'd like to be certain our code works correctly in both valid and invalid situations. Take, for example, the movie lens hook from Chapter 8, which holds a method, get_ratings. The method accepts several arguments. One of them is batch_size, which controls the size of batches requested from the API. You can imagine valid input would be any positive number, maybe with some upper limit. But what if the user provides a negative number, for example, -3? Maybe the API handles the invalid batch size correctly and returns an HTTP error such as 400 or 422. But how does the movie lens hook respond to that? Sensible options might be input value handling before even sending the request, or proper error handling if the API returns an error. This behavior is what we want to check. Let's continue with the work of Chapter 8 and implement a movie lens popularity operator, which is an operator returning the top n popular movies between two given dates. How do we test the correctness of this movie lens popularity operator? First, we could test it as a whole by simply running the operator with given values and check if the result is as expected. To do this, we require a couple of PyTest components to run the operator by itself, outside a live airflow system and inside a unit test. This allows us to run the operator under different circumstances and validate whether it behaves correctly. Section 9.1.4 PyTest Project Structure. With PyTest, a test script requires to be prefixed with test underscore. Just like the directory structure, we also mimic the file names. So a test for code in movielens underscore operator.py would be stored in a file named test underscore movielens underscore operator.py. Inside this file, we create a function to be called as a test. In this example, we instantiate the bash operator and call the execute function, given an empty context, empty dict. When Airflow runs your operator in a live setting, several things happen before and after, such as rendering templated variables and setting up the task instance context and providing it to the operator. In this test, we are not running in a live setting, but calling the execute method directly. This is the lowest level function you can call to run an operator, and it's the method every operator implements to perform its functionality. We don't need any task instance context to run the bash operator, therefore we provide it an empty context. In the case the test depends on processing something from the task instance context, we could fill it with the required keys and values. Footnote 3. The xcom underscore push equals true argument returns std out in the bash underscore command as string, which we use in this test to fetch and validate the bash underscore command. In a live Airflow setup, any object returned by an operator is automatically pushed to xcom. Let's run this test. Now let's apply this to the movielens popularity operator. The first thing that appears is red text telling us the operator is missing a required argument. Now we see the test failed because we're missing the required argument con underscore ID, which points to the connection ID in the metastore. But how do you provide this in a test? Tests should be isolated from each other. They should not be able to influence the results of other tests, so a database shared between tests is not an ideal situation. In this case, mocking comes to the rescue. Mocking is faking certain operations or objects. For example, the call to a database that is expected to exist in a production setting, but not while testing, could be faked or mocked by telling Python to return a certain value instead of making the actual call to the non-existent during testing database. This allows you to develop and run tests without requiring a connection to external systems. It requires insight into the internals of whatever it is you're testing, and thus sometimes requires you to dive into third-party code. PyTest has a set of supporting plugins, not officially by PyTest, which ease the usage of concepts such as mocking. For this, we can install the pytest-mock Python package. Pytest-mock is a Python package that provides a tiny convenience wrapper around the built-in mock package. To use it, pass an argument named mocker to your test function, which is the entry point for using anything in the pytest-mock package. Footnote 4. If you want to type your arguments, mocker is of type pytest_mock.mockfixture. With this code, the get_connection call on the movielens hook is monkey-patched, substituting its functionality at runtime to return the given object instead of querying the Airflow metastore, and executing movielens hook.get_connection won't fail when running the test, since no call to the non-existent database is made during testing, but instead the predefined expected connection object is returned. This example shows how to substitute a call to an external system, the Airflow metastore, at test time by returning a predefined connection object. What if you want to validate the call is actually made in your test? We can assign the patched object to a variable that holds several properties collected when calling the patched object. Say we would like to ensure the get_connection method is called once and only once, and the con_ID argument provided to get_connection holds the same value as provided to the movie lens popularity operator. Assigning the return value of mocker.patch.object to a variable named mock_get will capture all calls made to the mocked object and gives us the possibility of verifying the given input, number of calls, and more. In this example, we assert if call_count can verify that the movie lens popularity operator doesn't accidentally make multiple calls to the Airflow metastore in a live setting. Also, since we provide the con_id testcon to the movie lens popularity operator, we expect this con_id to be requested from the Airflow metastore, which we validate with assert_called_with. The mock_get object holds more properties to verify. For example, a called property to simply assert whether the object was called, any number of times, figure 9.6. Footnote 5. A convenience method exists for these two asserts named assert_called_once_with. One of the biggest pitfalls with mocking in Python is mocking the incorrect object. In the example code, we are mocking the get_connection method. This method is called on the movie lens hook, which inherits from the base hook, airflow.hooks.base package. The get_connection method is defined on the base hook. Intuitively, you would therefore probably mock basehook.get_connection. However, this is incorrect. The correct way to mock in Python is to mock the location where it is being called, and not where it is defined. Let's illustrate this in code. Footnote 6. This is explained in the Python documentation here. It is also demonstrated in this link. Section 9.1.5. Testing with files on disk. Consider an operator that reads one file holding a list of JSONs and writes these to CSV format, figure 9.7. The operator for this operation could look as follows. This JSON to CSV operator takes two input arguments, the input JSON path and the output CSV path. To test this operator, we could store a static file in our test directory to use as input for the test. But where do we store the output file? In Python, we have the temp file module for tasks involving temporary storage. It leaves no remainders on your file system since the directory and its contents are wiped after usage. Once again, PyTest provides a convenient access point to this module named tmp_dir, gives os.path object, and tmp_path gives pathlib object. Let's view an example using tmp_path. Upon starting the test, a temporary directory is created. The tmp_path argument actually refers to a function, which is executed for each test it is called in. In PyTest, these are called fixtures. See this link. While fixtures bear some resemblance with unitests, setup, and teardown methods, they allow for greater flexibility because fixtures can be mixed and matched. For example, one fixture could initialize a temporary directory for all tests in a class, while another fixture only initializes for a single test. The default scope of fixtures is every test function. We can see this by printing the path and running different tests, or even the same test twice. Footnote 7. Look up PyTest scope if you're interested in learning how to share fixtures across tests. This will print, respectively, this and this. There are other fixtures to use, and PyTest fixtures have many features that are not demonstrated in this book. If you're serious about all PyTest features, it helps to go over the documentation. Section 9.2. Working with DAGs and task context in tests. Some operators require more context, for example, templating of variables, or usage of the task instance context for execution. We cannot simply run operator.execute context equals curly brackets like we did in the previous examples because we provide no task context to the operator, which it needs to perform its code. In these cases, we would like to run the operator in a more realistic scenario, as if Airflow were to actually run a task in a live system and thus create a task instance context, template all variables, and so on. Figure 9.8 shows the steps that are performed when a task is executed in Airflow. Footnote 8 in task instance _run_raw_task. As you can see, step 5 is the only one we've run in the examples so far, listings 9.15, 9.17, and 9.20. If running a live Airflow system, many more steps are performed when executing an operator, some of which we need to execute to test, for example, correct templating. Say we implemented an operator that pulls movie ratings between two given dates, which the user can provide via templated variables. This operator is not testable, as in the previous examples, since it potentially requires the task instance context to execute. For example, the output_path argument could be provided as /output/ds_.json, and the ds variable is not available when testing with operator.execute context equals curly brackets. So for this, we'll call the actual method Airflow itself also uses to start a task, which is operator.run, a method on the base operator class. To use it, the operator must be assigned to a DAG, while the previous example could be run as is, without creating a DAG for testing purposes. In order to use run, we need to provide a DAG to the operator, because when Airflow runs a task, it refers to the DAG object on several occasions, for example, when building up the task instance context. We could define a DAG in our tests as follows. The values we provide to the test DAG doesn't matter, but we'll refer to these while asserting the results of the operator. Next, we can define our task and run it. If you run the test as we've defined it now, you will probably encounter an error similar to the following listing. As you can tell from the error message, there's something wrong in the Airflow metastore. To run a task, Airflow queries the database for several pieces of information, such as previous task instances with the same execution date. But if you haven't initialized the Airflow database, Airflow DB init in the path Airflow_home is set to approximately /Airflow if not set, or configured Airflow to a running database, then it will have no database to read or write. So also when testing, we will need a metastore. There are several approaches to deal with the metastore during testing. First, hypothetically, we could mock every single database call, as shown before, when querying for connection credentials.